Hello, welcome to PhyzQuest. So this is the solution video for CSIR NET December 2019 Part C, question number 5. The question is, assume that the noise spectral density at any given frequency in a current amplifier is independent of frequency. The bandwidth of measurement is changed from 1 Hz to 10 Hz. So we need to find out the ratio of the RMS noise current before and after the bandwidth modification. 4 options are given and we need to choose the correct option. So let's get started. So this question comes from the section electronics and the concept involved here is operational amplifier. So this question is about the frequency characteristic of the operational amplifier noise. The noise we are talking about is intrinsic to the operational amplifier, and it is associated with the passive components like noise due to the input or feedback resistor, or intrinsic voltage noise or current noise, etc. When we talk about a noise spectrum, it is usually about power, not voltage. That is how the power is distributed in the frequency range. It is expressed in terms of total power per the frequency range considered. So the unit is watts per hertz. Now when the noise spectrum is expressed in terms of voltage or current, power is voltage square over resistance or current square multiplied with the resistance. So while expressing noise, we have to take the square root of the frequency range in case of voltage or current. Now the graph of the frequency characteristic of the operational amplifier noise spectrum will be like this. So as you can see, the graph has two distinct regions. One is the low frequency region, which is proportional to 1 by f and is called the pink region, and the second region is of the higher frequency and it is independent, where noise is constant and independent of frequency. This is called white noise region. The color of the noise is decided by the spectrum's dependence to the power of the frequency. For 1 by f it is pink and for no dependence it is white. The point in the frequency spectrum here where the pink noise and the white noise are equal, it's called the corner frequency. In other words, the frequency at which the noise starts to increase is called the corner frequency. So this is obtained by extrapolating a horizontal line from the white noise portion of the curve and a straight line from the pink noise portion of the curve, and the point at which the two lines intersect each other gives the corner frequency. So the lower this corner frequency, the better is the operational amplifier. Now this noise spectral density, this curve, gives the peak value of the voltage or current, and the question here is about the RMS value. So to convert the peak to RMS, you must square the peak value, integrate across the desired bandwidth and take the square root of the result. Here we have two regions. If the total bandwidth of the frequency is for low frequency, suppose the total bandwidth is from FL low frequency to FH high frequency. So for pink region, the bandwidth will be from FL to FC. So the general equation for the noise spectral density for the pink region is equal to K square root of FC square root of 1 by F, where K is the level of the white noise and the FC is the corner frequency. So K you can find out, that is here the point at which it crosses the value it intersect at this axis. That will give you the K value. So here now applying the peak to RMS conversion method, as I said, the RMS noise for the pink region for the bandwidth FL to FC, this will be equal to K square root of FC square root of integration from FL to FC 1 by F dF, which upon calculation will give you K square root of FC ln FC by FL. So next region is the white noise region. That is for the bandwidth fc to fh. So for that the RMS noise will be equal to k square root of fc minus fh. So the total RMS noise spectral density from FL to FH will be the square root of the sum of the squares of both the noise terms. That means you have to first of all make a sum of the squares. So you have to square both the terms, take the sum, and then make the square root of the whole term. So this will be equal to k square root of fc ln fc by fl plus fc minus fh. This will be the final term. Now in the question it is assumed that the noise spectral density is independent of frequency, which means that the question only concerns with the white noise region. So that means we can omit this term. So now the RMS noise will be equal to, the total RMS noise will be equal to in the white noise region k is square root of fc minus fh. That is actually k into square root of the bandwidth. So it is given that the bandwidth measurement is changed from 1 Hz to 10 Hz. We need to calculate the ratio of the RMS noise before and after the bandwidth modification. So before bandwidth modification, this fc minus fh is 1 Hz. So RMS noise current A is equal to k square root of 1, and after bandwidth modification the fc minus fh, that is the bandwidth, is 10 Hz. So the RMS noise current B is equal to k square root of 10. So we need to calculate the ratio of both the RMS noise current, that is A by A, the ratio A by B. So the ratio A by B is equal to 1 by square root of 10. So this is our answer. Now let's check the option. Now if you check the option, you can see that option B is matching with our result. So correct answer for this question is option B.